Math 175, Calculus 1, limits at infinity. Any questions about homework problems or other questions about calculus before we start today's lesson?
I have a question.
Yes, go ahead.
It's from exercise 4.4.
Can you speak up a little bit? It's hard for me to hear you.
It's question 11 from exercise 4.4.
4.4.
In addition 5.
So this is 24 over x squared plus 12?
No, it's 2x minus tan x.
What edition of the book do you have?
It's edition 6.
So this is to determine concavity, where a graph is concave up or concave down?
Yeah.
And so tell me what the function is. F of x equals what?
2x minus tan of x
I'm sorry, 2x.
minus tan of x.
Okay. Just that?
Just that, yeah.
Okay. So we want to determine where the graph is concave upward and concave downward, which means we have to look at the second derivative. So the first derivative is 2, and the derivative of the tangent is secant squared. And the second derivative of 2 is 0. So the derivative of minus the secant squared is minus 2 times the secant of x times the derivative of the secant, which is the secant times the tangent. So this is minus 2 secant squared x tangent x. And we want to know where this is concave up and where it's concave down. So the sign of this, so if secant squared x is not either 0 or infinity, then it's positive. So f prime of x has the same plus or minus sign as the tangent of x. Is that okay? Are there any questions about this?
No, thank you.
So let's recall, what does the graph of y equal the tangent of x look like? So it's 0, it's 0. So tangent is sine over cosine. So when the sine is 0, which is at 0, it's 0. As you go from 0 to pi over 2, you're still in the first quadrant. This is positive. The sine of x is approaching 1. The cosine of x is going to 0. So this is going to infinity. And in the fourth quadrant, as you go from minus pi over 2 to 0, the cosine is positive and the sine is negative. And as you approach minus pi over 2, the cosine is going to 0. So the function looks like this. So what can we say? So first of all, this function, so f of x equal 2x minus the tangent of x. This is defined, it's periodic. Well, sorry, forget periodic, but it's defined for minus pi over 2 less than x less than 0. Because, sorry, let me say this correctly. Minus pi over 2 less than x less than pi over 2. And in this region, f of x is concave up, where the derivative is positive, which means where minus tangent of x is greater than 0, which means tangent x is negative. So this is for x between minus pi over 2 and 0. And f of x is concave down, where the derivative is negative, which means where the tangent is positive. So that's between 0 less than x less than pi over 2. And that's what we get. So if the function is 2x minus the tangent of x, you differentiate it once, you get 2 minus secant squared. You differentiate it a second time, you get minus 2 secant x times the derivative of the secant, which is secant times the tangent. Secant times secant is secant squared. So unless this is 0 or infinity, this is positive. So the second derivative is minus 2 times a positive number times the tangent. So where the tangent is positive, the second derivative is negative, and the curve is concave down. Where the tangent is positive, the second derivative is negative, and the curve is concave up. So that gives us, that's the answer, I guess. Other questions that I can go over? In that same section on concavity, let me do the homework problem 47. So in problem 47, we have f of x equal to a cubic, x cubed minus 3x squared plus 3. We want to find the relative extrema, that is relative maxima and relative minima, using the second derivative test where we have to. So let's see. We take the first derivative, 3x squared minus 6x. So that's 3x times x minus 2. So this is equal to 0 when x equals 0 and x equal 2. So these are the critical numbers. What's the second derivative? 6x minus 6. If we evaluate the second derivative at 0, we get minus 6, which is negative. So x equals 0 is a relative maximum. The second derivative test says if the first derivative is 0 and the second derivative is negative, you have a relative maximum. If we compute the second derivative at 2, we get 6 times 2 minus 6, which is 12 minus 6, which is 6, which is positive. So x equal 2 is a relative minimum. So this is a nice example of the use of the second derivative test. Let's look at another one. Suppose we have number 43. 43, we have the function f of x equals x minus 5 squared. The first derivative is 2 times x minus 5, and that's equal to 0 precisely when x equals 5. So this is the only critical number. The second derivative, 2x minus 5, the derivative is 2, which is positive. So x equal 5 is a relative minimum. And of course, this is just the graph of a parabola, translated over 5 units. This is just the parabola that looks like that. And that's the point x equal 5. And you can see clearly that's a minimum. It's the vertex of the parabola. Let me do one more because these are important. Number 55, it's not one of the homework, but it's a nice looking problem. F of x is x plus 4 over x. So what can we say about the relative extrema? The first derivative is 1 minus 4 over x squared, or 1 minus 4 times x to the negative 2. This equals 0 when? If and only if 1 minus 4 over x squared equals 0, which is the same as x squared equals 4, or x equal plus or minus 2. So we have two critical points, plus 2 and minus 2. What's the second derivative? If this is the first derivative, the second derivative is minus 4. The derivative of x to the minus 2 is minus 2x to the minus 3. So that's 8 x to the minus 3, 8 over x cubed. If you evaluate this at plus 2, 8 over 2 cubed is 1, which is positive. So x equal 2 has to be a relative minimum. If you evaluate this at minus 2, you get 8 over minus 8, which is minus 1, which is negative. So minus 2 has to be a relative maximum. And that's what it is. In fact, if you were to graph this function, it would look something like this. That's 2. At x equal plus 2, you have a minimum. This is minus 2. At minus 2, you have a relative maximum. And the function is undefined at x equals 0. Any questions about this? These are very important problems. It is 100% certain that problems like this will be on the second exam, which is in about 2 weeks, and also on the departmental final.
I have a question.
Go ahead.
So for these type of question, we use a second derivative test, right? So
Yep.
like when we used f, that's the second derivative test.
The second derivative test says if you find a point x where the first derivative is 0, then you look at the second derivative. If the second derivative is positive, that means you have a relative minimum. If the second derivative is negative, that means you have a relative maximum. If the second derivative is 0, then you get no information from the test. So there are 3 cases. And in one case, you know you have a max. In the other case, you know you have a min. In the third case, you just don't know, you don't learn anything from the test. It could be a maximum, it could be a minimum, it could be neither one. But the second derivative test allows you to distinguish relative maxima from relative minima in many, many cases. Okay. All right. If there are no further questions about the second derivative test and concavity, let's look at section 4.5.
I have a question. I'm sorry, I just found it.
All right, no, that's good. Go ahead.
It's number 11 in version 5.
All right, so you have to tell me the problem because I don't have the book.
Oh, f of x equals 24 over x squared plus 12.
Okay, so in the 5th edition, which is what the homework is key to, this is a homework problem.
Yeah,
It's number 11.
4.4.
Excuse me?
It's section 4.4.
Yeah, right. So that's number 11 in section 5. That's one of the homework problems. It's f of x equals 24 over x squared plus 2. And we want to determine where the graph is concave up and where it's concave down. So we take the first derivative. So we can either use the quotient rule, or we can say this is the same as 24 x squared plus 2 to the minus 1 and use the chain rules. You get the same answer no matter what you do. It's just a matter of choice. By the chain rule, this is 24 minus 1 times x squared plus 2 to the minus 2 times the derivative of x squared, which is 2x. So you can write this, if you like, as minus 24x over x squared plus 2 squared. And this is equal to 0 if and only if this is always positive, x equals 0. So there's one critical number for this function. That's just interesting to note. Let's look at the second derivative. Maybe for the second derivative, I'll use the quotient rule. The second derivative is minus the derivative. I'll just write this as minus 24 so I don't have to worry about the constants. This is minus 24 times x over x squared plus 2 squared. So, oops, I'm sorry. I wrote 24 over x squared plus 2, but someone should have pointed out I wrote the problem down wrong. It's not x squared plus 20, it's x squared plus 12. That's just a 12 there. So that doesn't change anything except that. Okay. 24 over x squared plus 12. The derivative is 24 minus x squared plus 12 to the minus 2 times 2x. So, oops, again, I have to do my arithmetic correctly. 2 times 24 is 48, minus 48x over x squared plus 12 squared, or minus 48 times x over x squared plus 12 squared. Right, let me try and make this a little bit more legible. X squared plus 12 squared. And again, the only critical number is x equals 0. but we need to differentiate the derivative to get the second derivative. So that's minus 48 times the derivative of this. You square the denominator. So x squared plus 12 squared is x squared plus 12 to the fourth. It's the derivative of the numerator, which is 1 times the denominator, minus the numerator times the derivative of the denominator, which is 2 times x squared plus 12 times the derivative of x squared plus 12, which is 2x. So this is minus 48. I have here x squared plus 12 squared minus 2x times 2x, that's 4x squared, times x squared plus 12 over x squared plus 12 to the fourth. And if I factor out an x squared plus 12, I cancel one of these. I get minus 48 x squared plus 12 minus 4x squared over x squared plus 12 cubed. X squared minus 4x squared is minus 3x squared plus 12 over x squared plus 12 cubed. Minus times minus is plus. This is 48. 3x squared minus 12 over x squared plus 12 cubed. Or if I want to factor a 3 out of this, I get x squared minus 12 times 3 times 48. What's 3 times 48? 3 8 are 24, 144 over x squared plus 12 cubed. So if I did the calculus correctly, you need to check, this is the second derivative. Now, this is always positive. X squared plus 12 is positive. Positive number squared is positive. 144 is positive. So the sign of this is completely determined by the sign of x squared minus 4. So f double prime is positive if x squared minus 4 is positive, which means x is either bigger than 2 or x is less than negative 2. And in this region, the curve is concave up, because that's where the derivative is positive. Second derivative is negative. When x squared minus 4 is negative, that means x squared is less than 4. That's the same as saying x is less than 2 and greater than negative 2. So in this area, in this interval, the curve is concave down.
So I have a question.
Yeah.
So over here it says negative 3x squared plus 16, and then it says 3x squared minus 12.
Sorry, there's no 16. I mean, you might, let's see. This is a 2. That's what you mean. Right?
Oh, okay.
Right. And let's just double check. So according to this analysis, my curve is concave up, concave down. Where? Let's see. Concave down for x between 2 and minus 2 and 2, x less than negative 2 or x greater than plus 2. What was our function? My function is f of x equals 24 over x squared plus 12. It's always positive. What does the graph look like? When x is 0, I get 24 over 12, which is 2. We already saw f prime of 0 when I differentiated the function, it was 0 only when x equals 0. That's the only critical number. So we might have a relative maximum or minimum there. The second derivative at 0, well, 0 is between -2 and 2. So this is negative. The curve is concave down at 0. Curve is concave up, starting at 2 and -2. What is f of 2 equal to? 24 over 2 squared plus 12. 24 over 4 plus 12. 24 over 16, which is 3/2. So at -2 and a +2, this takes on the value 3/2. And the curve, in fact, looks like this. It's concave up, then it's concave down, then it's concave up again. And x equal -2 and x equal +2, these are inflection points. Those are the points where the curve changes from concave up, concave down, concave up again. So this is really a very pretty example of concavity and the use of the second derivative to determine that. An inflection point is a point where a curve changes from concave up to concave down, or from concave down to concave up. And we see inflection points at +2 and -2. We also see something else very interesting here, because we see that as x goes to +infinity, this curve is decreasing to 0. So for this function, 24 over x squared plus 12, the limit as x goes to +infinity of f of x is 0. And similarly, as you go to -infinity, the limit of f of x as x goes to -infinity is also equal to 0. So these are examples of what we mean by limits at infinity. Let's look at another example of a function which has some sort of limiting behavior as you approach infinity. Suppose we look at the function f of x equals 3x squared over x squared plus 1. So let's make some observations first. Notice that x squared plus 1, x squared is always at least 0, so this is greater than or equal to 1 for all x. So this denominator is always positive. 3x squared is greater than 0 for all x different from 0. So this function is positive, strictly positive, for all x different from 0, and f of 0 is 3 times 0 over 0 plus 1. That's 0 over 1, that's 0. So without even using a derivative, we see we have a minimum at x equals 0. And if we numerically compute this function for large values of x, we'll see it has a certain kind of limiting behavior. If we use maple and graph the function, we'll see it has a limiting behavior. If we just use a little bit of high school algebra, we could say the following: 3x squared over x squared plus 1. This is the same as 3x squared. And let me add 3 and subtract 3 from the denominator. So I just put in 0. So this is 3x squared plus 3 minus 3 over x squared plus 1. 3x squared plus 3 is 3 times x squared plus 1 minus 3 over x squared plus 1. If we write that as two fractions, this over this, three x squared plus 1 over x squared plus 1 minus 3 over x squared plus 1. These cancel. So this function can also be written as 3 minus 3 over x squared plus 1. And now it's clear what happens. The limit of f of x as x goes to either plus infinity or minus infinity. I'll just write plus or minus infinity. It's 3 minus this. The denominator is getting bigger and bigger. So this is going to 0. So this limit is equal to 3. And if we were to graph this function, it's 0 at 0. It looks like this. As x goes to infinity, f of x is approaching 3. And as x goes to minus infinity, f of x is also approaching 3. So we have these two limits at infinity. And
I have a question. Where did the 3 come from? Where it says 3x squared plus 3 minus 3 over x squared plus 1?
I mean, how did I get from here to here?
Yes.
Well, what is 3 minus 3 equal to?
3
0.
minus 3?
0, right? 3 minus 3 is 0.
Yes.
You can always add 0. So I just added
Okay.
0. Now, why did I do that? Because I saw if I do that, I can write it like this. Cancel the x squared plus 1 from the first term. I can rewrite my function in this. So this was a convenient technical way to find another way to express the same function in order to understand what happens as x goes to infinity. Right? Now, if you're asking, is there a rule that told me to do this? The answer is no. How did I know to do it? Well, you can say a lucky guess or imagination or creativity or whatever. I mean, you know, mathematics isn't just following a set of rules. It requires some, requires some imagination and creativity to figure out how to solve a problem. So some things are automatic. You know, if you're given two 5-digit numbers and told how to and asked to multiply them, it's a long calculation, but it's mechanical. You don't have to think at all. You just have to do the arithmetic correctly. But sometimes it's not just that it's mechanical. You know, you need some skill to solve a problem. And you acquire that skill by spending a lot of time doing homework problems and other problems. But yeah, so you might say, there was no rule that told me to do this, but if I did it, I could figure out very easily how to solve the problem. That's why I did it. You know, there are other ways you could have done it. For example, let me I could have done this. I could have said f of x is 3x squared over x squared plus 1. if I divide by x squared, I get 3 over 1 plus 1 over x squared. And this goes to 0 as x goes to infinity, which implies that f of x goes to 3 as x goes to infinity. That would have been another way to do it. There's almost never just one way to solve a problem. Any other questions about that? I mean, I'm happy to explain it more if necessary. So there's a formal definition of limit at infinity. And it is the following. So to say that the limit of a function f of x as x goes to infinity is equal to L if for any number, no matter how small, call it epsilon greater than 0, there exists a number m greater than 0 such that the difference between f of x and L is less than epsilon for all x greater than m. So geometrically, what that means is if you're looking at your function, and this is the horizontal line y equals L, you're looking at the graph of the function, there's some number m, so that as long as x is bigger than m, see this is L, the graph of your function is always no bigger than epsilon away. This is L plus epsilon, this is L minus epsilon. So this is this little strip of thickness 2 epsilon, and the graph of the function is always in there forever. And there is an analogous definition of what it means for the limit of f of x as x goes to minus infinity to equal L. And it's almost the same thing. It's just what you would expect. For every epsilon greater than 0, there exists a number n less than 0, such that f of x minus L in absolute value is less than epsilon for x less than n. In other words, this is y equals L, and then you have this little strip around it of L plus epsilon, L minus epsilon. Here's n, and for all x less than n, the graph of this function, whatever it looks like over there, is squeezed between L plus epsilon and L minus epsilon as for all x less than n. So this is just a formal way of writing down your intuition about what it means to have a limit as you go to infinity. And if L is a limit as x goes to either plus infinity or minus infinity, then we say that in this case, the horizontal line y equal L is a horizontal asymptote of the graph of f. So this is the definition of limit at infinity, and this is the definition of a horizontal asymptote. And to give the two fundamental examples of limits at infinity and horizontal asymptotes, so let R be greater than 0, then the limit as x goes to plus infinity of 1 over x to the r is 0. Because the graph looks like that. And the limit as x goes to minus infinity of 1 over x to the r is also 0. Now, r could be okay. This is example 1. And example 2, remember the graph of the function y equal e to the x. Looks like that. And remember the graph of the function y equals e to the minus x. It looks like that. So the limit as x goes to plus infinity of e to the minus x is 0. And the limit as x goes to minus infinity of e to the minus x is also 0. Okay. Any questions about this? And then there's also the following sort of basic fact that if the limit of f of x as x goes to infinity and the limit of g of x as x goes to infinity both exist, then if we take f of x plus g of x, the limit of this as x goes to infinity is the sum of the limits of f of x and g of x individually. So the limit of the sum is the sum of the limits even when x is going to infinity. And the same with products. Limit of f of x times g of x is the limit of f of x times the limit of g of x. So if you have two functions, f and g, and their limits as you go to infinity both exist, the limit of the sum is the sum of the limits. The limit of the product is the product of the limits. Okay. What about other familiar functions? Well, what's the limit of f of x, limit of the sine of x as x goes to infinity? Sine of x looks like that. Oscillates between 1 and minus 1. So this limit does not exist. What about the limit as x goes to infinity of sine x over x? That's interesting. So if we look at the graph, This is the graph of y equals 1 over x. This is the graph of y equals minus 1 over x. So sine x over x, it's at most, for any x, it's at most 1 over x and at least minus 1 over x. And in fact, this function is oscillating. If there's a sign there, it's oscillating. But the oscillations are damped, and this limit is 0. What is the limit as x goes to infinity of 5 minus 2 over x squared? Well, the limit as x goes to infinity of 5, and the limit of 2 over x squared as x goes to infinity both exist. This is the constant function 5. That limit is 5. 2 over x squared goes to 0. That limit is 0. So the answer is 5. Any questions about these? These are interesting. What about the limit as x goes to infinity? 3 over e to the x. That's the limit as x goes to infinity. 1 over e to the x is e to the minus x. So that's the limit as x goes to infinity of the constant function 3. The limit as x goes to infinity, e to the minus x. The limit of the constant function 3 is 3, but the limit of e to the minus x, as we saw, is 0, and 3 times 0 is 0. So the limit is 0. All right. Let's look at a more interesting problem. Limit as x goes to infinity, 2x minus 1 over x plus 1. Now this is a little more complicated because the numerator and the denominator both go to infinity separately. So infinity over infinity doesn't make any sense. But we can do the following trick, if you like. Divide the numerator by 2 and divide denominator by 2. You get 2 minus 1 over x over 1 plus 1 over x. And now when you do that, it's clear what happens because as x goes to infinity, 1
Professor, you
over x,
mean divided by x?
yes, I divided the
Oh,
numerator, or if you like, I factored an x out of the numerator and I factored an x out of the denominator and canceled the x's. But algebraically, this is equal to this, right? Just check. But 1 over x goes to 0 as x goes to infinity. So this limit is 2 over 1, or 2. And we could figure out the limit. This is a very useful technique. Let's look at three more examples. Suppose we look at 2x plus 5 over 3x squared plus 1 as x goes to infinity. Limit of 2x squared plus 5 over 3x squared plus 1 as x goes to infinity. Limit of 2x cubed plus 5 over 3x squared plus 1 as x goes to infinity. So in these three problems, the denominators are the same. The numerators are almost the same. All I did is as I go from one to the next, I increase the power of x by 1. X squared, x cubed. So one way to approach these things when you have a rational function, that's what this is, that's what these are, quotients of polynomials, is divide by the highest power of x. Here the highest power of x is x squared. So if you divide the denominator by x squared, you get 3 plus 1 over x squared. If you divide the numerator by x squared, you get 2 over x plus 5 over x squared. What happens is x goes to infinity. These two go to 0. This is 3. This goes to 0. I get 0 over 3, which is 0. So this limit is equal to 0. Let's see here again, the highest power of x is x squared. If I divide by x squared, numerator and denominator, I still get in the denominator 3 plus 1 over x squared. If I divide this by x squared, I get 2 plus 5 over x squared. As x goes to infinity, this goes to 2 and this goes to 0. This goes to 3 and this goes to 0. So I just get 2/3. So that limit is 2/3. In this last case, if I divide by x cubed, let's see what happens. If I divide the numerator by x cubed, I get 2 plus 5 over x cubed. If I divide the denominator by x cubed, I get 3 over x plus 1 over x cubed. What happens as x goes to infinity? I get 2 plus 0 over 0 plus 0. That's infinity or undefined, whatever you want to call it, but does not, the limit does not exist, or the limit is infinite. You can say either one. An alternate way of doing this would be to divide numerator and denominator by x squared. Just a matter of choice. If I divide by x squared, I get 3 plus 1 over x squared in the denominator. I get 2x plus 5 over x squared in the numerator. As x goes to 0, this is going to infinity over 3 infinity. Again, you can say in both cases, either the limit is infinity or the limit does not exist. I would be happy with either one.
Professor, can you move the paper a little bit? Thank you.
See, here's a nice example. Suppose we take f of x equal to 1 over 1 plus e to the minus x. So for this function, remember, the limit as x goes to infinity of e to the minus x is 0. So if I take the limit of this function f of x as x goes to infinity, that's the limit as x goes to infinity of one over 1 plus e to the minus x. The numerator, it's just 1, it's constant. The limit of 1 plus e to the minus x is 1 plus 0. So this is 1 over 1 is 1. So the limit as x goes to infinity for this function is 1. It's approaching 1. What about the limit of this function as x goes to minus infinity? So that's the limit as x goes to minus infinity of 1 over 1 plus e to the minus x. So the limit of 1 is 1. And e to the minus x, as x goes to minus infinity, that means minus x is going to plus infinity. E to the x is going to infinity. This limit is 0. Okay? This denominator is getting bigger and bigger and bigger. So this is y equals 0. So this function, so f of x equal 1 over e to the minus x, 1 plus e to the minus x, has 2 horizontal asymptotes, y equals 0 and y equal 1. So it's easy to think that if a function has a horizontal asymptote, it's the same whether you go to plus infinity or minus infinity. But this is a pretty example of a function that has 2 different horizontal asymptotes. It has one limit as you go to plus infinity, and it has a limit, but a different limit as you go to negative infinity. Okay. So there is a formal definition of what it means for a function to have the limit infinity as x goes to infinity. It's slightly different from the definition we gave for the finite limit or a horizontal asymptote at infinity. And it's the following. So this is the definition of infinite limits at infinity. So that f of x be defined for all x greater than a. That means on the interval from a to infinity, if you like interval notation. So to say that the limit of f of x as x goes to infinity is equal to infinity means the following. For every m greater than 0, no matter how big, there exists a number n greater than 0, such that f of x is greater than m for all x greater than n. So if I pick some big number m, whatever is the graph of my function, as soon as x is bigger than n, the graph of the function is always above m. No matter how high I make m go, from some point on, the graph of the function is always above that horizontal line. And there is the analogous statement for the limit of f of x to be equal to minus infinity as x goes to infinity, namely, for all m negative, for all m less than 0, there exists a positive n such that f of x is less than minus m for all x bigger than n. So for example, if we look at the function f of x equal x cubed, graph looks like that. The limit of x cubed as x goes to infinity is plus infinity. And the limit of x cubed as x goes to minus infinity is minus infinity. Okay. Let me do just one or two more examples, and then we'll be done for today. So suppose we take the function f of x equals 2x squared minus 4x over x plus 1, and we want to find the limit of this function as x goes to infinity. So one way to do this is a method that's suggested in the book, there are other ways, is to do long division. Suppose we divide x plus 1 into 2x squared minus 4x. Let's see, what do we get? 2x, that's 2x squared plus 2x. You subtract, you get minus 6x. So what that says is that 2x squared minus 4x over x plus 1 is equal to the quotient 2x, and the remainder is minus 6x. So this is minus 6x over x plus 1. So this is the limit as x goes to infinity of 2x minus 6x over x plus 1. This approaches 6, but this is going to infinity. So the limit is equal to infinity. Oops, actually, I should have done this one more step. X plus 1 goes into this minus 6 times. So we get minus 6x minus 6 over 6. So, oops, this would have been better. So 2x squared minus 4x over x plus 1 is 2x minus 6 plus 6 over x plus 1. So the limit of 2x squared minus 4x over x plus 1 is the limit as x goes to infinity. 2x minus 6 plus 6 over x plus 1. this piece goes to 0. This goes to -6, but 2x is going up to infinity. So the limit's infinity. And if I were to take the limit as x goes to -infinity, 2x squared minus 4x over x plus 1, that's the limit, x goes to -infinity, of 2x minus 6 plus 6 over x plus 1. This goes to 0. This goes to -6. But as x goes to -infinity, 2x goes to -infinity. So this limit is -infinity. So whatever the graph of this function looks like, it's like going out to +infinity as x goes to +infinity, and it's going to -infinity as x goes to -infinity. Any questions about any of this? So there's only one more topic that's covered before the second exam. That's what we will do on Wednesday, which is optimization problems, which are important examples of the uses of calculus in applied situations. So on Wednesday this week, we do lesson 21 on optimization. Next Monday is a review for the second exam. And the second exam itself will be 9 o'clock on Wednesday, November 18th. That's the schedule. And immediately after the second exam, we study integration. We learn how to do definite integrals and indefinite integrals. Okay. Any questions about anything we did today? Okay. Then I will be here Wednesday at 9. See everybody then. Bye.
Bye, Professor. See
Thank
you.
you.